atoms and awesome energy. Everything around us, from the chair you're sitting on to the air you're breathing, even you, is made of tiny, tiny things called atoms. Think of them as super small building blocks, far too small to see with just your eyes. These atoms are like mini solar systems. At the very center of each atom is an even tinier part called the nucleus. The nucleus is packed with even smaller particles called protons and neutrons. Whizzing around the nucleus, like planets around the sun, are other particles called electrons. It's a busy, busy world down there at the atomic level, full of energy and motion, all fundamental to how our universe works. Now, the nucleus, that central part of the atom, holds an incredible amount of energy. It's called nuclear energy, and it's like a tightly coiled spring, just waiting for a chance to release its power. Scientists discovered that if you can carefully persuade a nucleus to change, for example by splitting it apart, it can release a tremendous burst of this stored energy, mostly in the form of heat. This isn't a chemical reaction like burning wood, it's a nuclear reaction, happening right inside the atom's core. It's this very special energy that we can harness in nuclear power plants to make electricity for our homes, schools, and hospitals. The idea of getting energy from atoms might sound like something out of a science fiction film, but it's real science, and it's happening right now. The particular type of atom we often use in nuclear power is a heavy one, like uranium. Uranium atoms have very large nuclei, which makes them a bit wobbly and easier to split compared to lighter atoms. When we talk about nuclear energy, we're usually talking about the energy that holds the nucleus together, known as the strong nuclear force. It's one of the fundamental forces of nature, and it's incredibly powerful over very short distances, like those inside an atom's nucleus. So, to recap, atoms are the basic building blocks of everything. They have a central nucleus packed with energy. If we can unlock that energy, we get nuclear energy, which is a very powerful source of heat. This heat is the key ingredient that nuclear power plants use to start their amazing process of generating electricity. It's all about understanding these tiny particles and the immense power they hold within them. Science is all about exploring these wonders, from the smallest particles to the largest galaxies, and learning how to use that knowledge responsibly. So, how does a nuclear power plant actually turn that amazing atomic energy into the electricity that powers your telly or charges your phone? Well, it's a step-by-step process, a bit like a very clever energy-changing machine. The main goal is to take the heat energy released from atoms and convert it, through several stages, into electrical energy. Think of it as a chain reaction of energy transformations, each step carefully designed and controlled. It all starts with that special nuclear fuel, usually uranium, which holds the key to releasing a massive amount of heat when its atoms are split. The first big step happens inside the heart of the plant, a place called the nuclear reactor. This is where the magic, or rather the science of splitting atoms occurs in a controlled way. This splitting process is called nuclear fission, and it releases a lot of heat. The next step is to use this heat. The heat from the fission reaction is used to boil water and turn it into steam, just like a giant kettle, but much, much hotter and more powerful. This steam is incredibly important because it's going to be our workhorse, carrying the energy to the next stage of the process. Once we have this high-pressure steam, it's channeled through pipes to spin a machine called a turbine. Imagine a giant, super-efficient pinwheel. The steam pushes against the blades of the turbine, making it spin incredibly fast. This spinning motion is a form of mechanical energy. So we've gone from nuclear energy to heat energy, and now from heat energy in the steam to mechanical energy in the spinning turbine. It's a clever conversion, carefully engineered to capture as much energy as possible from that initial nuclear reaction, ensuring efficiency. Finally, the spinning turbine is connected by a shaft to another amazing machine called a generator. Inside the generator, the spinning motion is used to create electricity. It works using magnets and coils of wire. When the wire moves through a magnetic field, or a magnet moves near the wire, it creates an electric current. This is the electricity that then travels through power lines to our homes and businesses. So there you have it. Atoms split, heat is made, water boils, steam spins a turbine, the turbine spins a generator, and out comes electricity. It's a fascinating journey of energy. let's dive a bit deeper into the most important part of a nuclear power plant, the reactor. The reactor is essentially a very strong, specially designed container where the nuclear chain reaction takes place safely and under strict control. It's built with thick walls, often made of steel and concrete, to keep all the radiation safely inside. Inside the reactor core, you'll find the nuclear fuel. This fuel isn't like the petrol you put in a car. It's usually made of uranium, formed into small ceramic pellets. These pellets are then stacked into long tubes called fuel rods. These fuel rods are bundled together to form fuel assemblies, and these assemblies are what make up the core of the reactor. It's within these fuel rods that the incredible process of nuclear fission happens. When a tiny particle called a neutron hits a uranium atom's nucleus, it can cause the nucleus to split into smaller atoms. This splitting, or fission, releases a burst of energy in the form of heat, and importantly, it also releases more neutrons. These new neutrons can then go on to hit other uranium atoms, causing them to split as well, and so on. This process, where one fission event triggers others, is called a nuclear chain reaction. If it's not controlled, it could happen too quickly and produce too much heat. That's where other key components come into play, which we'll talk about soon. The reactor's job is to sustain this chain reaction at a steady rate, continuously producing heat without letting it get out of hand. The amount of heat generated is enormous, far more than you could get from burning the same amount of coal or gas, which is why nuclear power is so potent. The design of the reactor is a marvel of engineering, ensuring that this powerful process is managed with extreme precision. Different types of reactors exist, but they all share the fundamental principle of using controlled nuclear fission to generate heat. Materials used in the reactor must be able to withstand high temperatures and radiation. The careful arrangement of the fuel, the control systems, and the cooling mechanisms all work together to make the reactor the powerhouse of the nuclear plant, a true testament to our understanding of atomic science. Now we know that the nuclear chain reaction inside the reactor produces a massive amount of heat. If this heat isn't managed properly, the reactor could overheat, which would be very dangerous indeed. So, two crucial elements in any nuclear reactor are the control rods and the coolant. Let's start with the control rods. These are long rods made of materials that are really good at absorbing neutrons, like cadmium or boron. Think of them as the brakes for the nuclear chain reaction. They can be moved in and out of the reactor core. When the control rods are inserted into the reactor core, they soak up many of the free neutrons that are flying around. Fewer neutrons mean fewer fissions, so the chain reaction slows down and less heat is produced. If you pull the control rods further out, more neutrons are available to cause fission, so the reaction speeds up and more heat is generated. This allows engineers to precisely control the rate of the nuclear reaction and the amount of power the reactor is producing. It's a delicate balancing act, ensuring just the right amount of fission is happening. Next up is the coolant. The coolant is a substance, usually water, but sometimes molten salt or gas, that circulates through the reactor core. Its main job is to absorb the intense heat generated by the fission process in the fuel rods. This heated coolant is then pumped out of the reactor core to where its heat can be used, typically to make steam. So, the coolant not only prevents the reactor from overheating, but also acts as a heat transfer medium, carrying the thermal energy to the next part of the power plant. It's a vital link in the energy conversion chain. Different types of reactors use different coolants. For example, pressurized water reactors use water kept under very high pressure so it can get super hot without boiling. Boiling water reactors allow the water to boil directly in the reactor core. Regardless of the type, the coolant system is a closed loop, meaning the same coolant is used over and over again, being cooled down after it has delivered its heat and then pumped back into the reactor to pick up more heat. This efficient system ensures continuous operation and heat transfer, all while keeping the reactor at a safe operating temperature. We've seen how the reactor generates immense heat, and how the coolant carries this heat away. So, what happens next with all that lovely hot coolant? Well, its primary job now is to make steam. In most nuclear power plants, especially pressurized water reactors, the superhot coolant from the reactor is pumped through pipes into a device called a steam generator. Inside the steam generator, there's a separate loop of water. The heat from the primary coolant, which came from the reactor, passes through the walls of the pipes and heats up this second loop of water. This second loop of water gets so hot that it boils vigorously and turns into high-pressure steam. It's a bit like a giant industrial-scale kettle, but instead of an electric element, the heat comes indirectly from the nuclear reactions. It's important that the water heated by the reactor, the primary coolant, doesn't mix directly with the water that becomes steam, especially in PWRs, to keep any potential radioactive materials contained within the reactor system. The steam generator acts as a heat exchanger, transferring thermal energy efficiently while keeping the two water systems separate. This high-pressure steam is the real workhorse of the power plant from this point onwards. It's incredibly energetic. Imagine the force of steam lifting the lid of a boiling pot. Now multiply that by thousands. This powerful steam is then directed through massive pipes toward the turbines. The design of these pipes and valves is crucial to ensure that the steam flows smoothly and efficiently, delivering its energy with minimal loss. The sheer volume and pressure of the steam are what will make the next stage of electricity generation possible, a true display of thermal power. The production of steam is a critical step because steam is an excellent medium for converting heat energy into mechanical energy. It can expand rapidly and exert a strong force, which is exactly what's needed to get the turbines moving. So the journey continues. Nuclear energy in the reactor core is converted to heat energy. This heat is transferred by the coolant to water in the steam generator, and this water transforms into powerful steam, ready to do some serious work. It's all about harnessing that initial atomic power in a usable form. Once that high-pressure steam has been created, it's time for it to do its main job, making things spin. The steam is blasted at incredible speed against a series of precisely shaped blades on a wheel, which is part of a machine called a turbine. Think of it like a giant high-tech windmill, but instead of wind, it's powerful steam that makes it turn. As the steam pushes against the turbine blades, it causes the shaft connected to the blades to rotate at very high speeds. This is where the heat energy of the steam is converted into mechanical energy, the energy of motion. Turbines in power plants are engineering marvels, often consisting of multiple stages with blades of varying sizes to extract as much energy as possible from the steam. As the steam passes through the turbine, it expands and cools, losing its energy to the spinning blades. The turbine shaft might spin thousands of times per minute, a blur of motion harnessing the immense power released from those tiny atoms. This rotation is the key to the next and final step in producing electricity. It's a direct link from the heat of the reactor to the generation of power. The spinning turbine shaft is directly connected to another amazing device called a generator. This is where the actual electricity is made. Inside the generator, the rotating shaft from the turbine spins large electromagnets, or coils of wire that act as magnets when electricity passes through them, inside massive coils of copper wire. According to the principles of electromagnetism, discovered by scientists like Michael Faraday, when a wire moves through a magnetic field or a magnet moves past a wire, an electrical current is induced in the wire. This is the fundamental principle behind nearly all large-scale electricity generation. So, as the turbine spins the generator, this movement creates a flow of electrons in the wires, and that flow of electrons is what we call electricity. This electricity is then stepped up to very high voltages by transformers, so it can be transmitted efficiently over long distances through power lines to our towns and cities, ready to power everything from streetlights to your computer. After the steam has done its work spinning the turbine, it is condensed back into water and pumped back to the steam generator to be heated up all over again, continuing the cycle. It's a continuous, powerful process. Nuclear power technology hasn't stood still since the first plants were built. Oh no, scientists and engineers are always working to make things better, safer, and more efficient. Modern nuclear power plants incorporate many advanced safety features and new reactor designs that are a world away from the earliest versions. One of the biggest focuses has been on passive safety systems. These are clever systems that work to keep the reactor safe automatically without needing human intervention or external power. For example, some designs use gravity or natural convection to circulate coolant if the normal pumps fail. These passive safety features mean that even if something unexpected happens, like a power cut to the plant itself, the reactor is designed to shut down and cool itself safely. This greatly reduces the risk of accidents. Furthermore, reactor materials have improved, and our understanding of how they behave under extreme conditions is much better. We also have much more sophisticated monitoring and control systems, using computers to constantly check on the reactor's status and make tiny adjustments to keep everything running smoothly and safely. It's all about layers of safety, one on top of another. There's also a lot of exciting research into brand new types of reactors, often called Generation 4 reactors or advanced reactors. These designs aim to be even safer, produce less waste, and even use different types of fuel, perhaps even some of the waste from older reactors. Some concepts include molten salt reactors, where the fuel is dissolved in hot salt, or high-temperature gas-cooled reactors. These could be more efficient and open up new uses for nuclear heat, like producing hydrogen fuel or desalinating seawater. The innovation in this field is truly remarkable. Another exciting development is the idea of small modular reactors, or SMRs. These are, as the name suggests, much smaller than traditional large nuclear reactors. They can be built in factories and then transported to where they are needed. This could make them quicker and cheaper to build. Because they are smaller, they might be suitable for powering smaller towns, remote industrial sites, or even replacing old coal plants. SMRs are designed with very high safety standards, often incorporating many of those passive safety features we talked about. It's a flexible and forward-thinking approach to nuclear energy. When we talk about energy, we also have to talk about its impact on our planet, especially concerning pollution and climate change. So how does nuclear power stack up? Well, one of the biggest advantages of nuclear power plants is that when they are operating to produce electricity, they don't release greenhouse gases like carbon dioxide. Carbon dioxide is the main gas responsible for trapping heat in our atmosphere and causing global warming. Fossil fuel power plants, those that burn coal, oil, or natural gas, release enormous amounts of carbon dioxide, as well as other pollutants like sulfur dioxide and nitrogen oxides, which cause acid rain and breathing problems. Nuclear power plants, on the other hand, produce electricity through nuclear fission, not by burning anything. So no smoke, no soot, and crucially, no carbon dioxide emissions directly from the electricity generation process itself. This makes nuclear power a very important tool if we want to reduce our carbon footprint and fight climate change. Of course, building a nuclear power plant, mining uranium, and processing the fuel does involve some energy use and emissions. But over the whole life cycle, nuclear power's carbon footprint is very low, comparable to renewable sources like wind and solar power. Now, what about nuclear waste? This is a very important question. Nuclear fission does produce radioactive waste. This waste needs to be managed very carefully because it can remain hazardous for a long time. Most nuclear waste is categorized as low-level or intermediate-level waste, which includes things like contaminated clothing or equipment. This can be managed quite safely. The high-level waste, which is mainly the used nuclear fuel, is much more radioactive and produces heat. This is stored very securely, often underwater in special pools at the power plant for several years to cool down. After cooling, this high-level waste is typically sealed in extremely strong, corrosion-resistant containers, often made of steel and concrete, and then stored in dedicated, secure facilities. Scientists and engineers are also working on long-term solutions, like deep geological repositories, which are specially designed underground sites where the waste can be safely isolated from the environment for thousands of years, until its radioactivity decays to safe levels. There's also research into advanced reactors that could potentially use some of this existing waste as fuel, reducing its volume and long-term hazard. It's a challenge, but one that is being tackled with serious science and engineering. So there you have it, a whirlwind tour of nuclear power, from tiny atoms to the electricity that lights up our world. We've seen how atoms hold incredible energy, how nuclear power plants carefully unlock that energy to make heat, how that heat creates steam to spin turbines, and how those turbines drive generators to produce electricity. It's a complex but fascinating process, all based on the amazing laws of physics and clever engineering. We've also touched upon new technologies making nuclear power safer and more versatile, and how it compares to other energy sources when it comes to air pollution. Nuclear energy is a powerful tool, and like any tool, it's important to understand how it works, its benefits, and its challenges. It offers a way to produce large amounts of electricity without releasing the greenhouse gases that are warming our planet. This is incredibly important as we look for ways to power our modern lives while also taking care of Earth. The science behind it is constantly evolving with new ideas and improvements emerging all the time, from advanced reactor designs to better ways of managing waste. It's a field full of discovery and innovation. The world needs bright young minds like yours to get curious about science, technology, engineering, and maths, what we often call STEM subjects. Whether it's understanding how atoms work, designing safer and more efficient machines, or figuring out the best ways to power our future sustainably, there are so many exciting challenges and opportunities waiting for you. Learning about different energy sources, including nuclear power, helps us all make informed decisions about our future and the kind of world we want to live in. Knowledge is power, after all. So, keep asking questions, be curious about how things work. Read books, watch science shows, visit museums, and talk to scientists and engineers if you get the chance. The more you learn, the more you'll understand the incredible universe around us and the role that science plays in shaping our lives and our future. Who knows? Maybe one day you'll be the scientist or engineer who makes the next big breakthrough in clean energy or helps solve one of the world's great challenges. The future is in your hands, so stay curious and keep exploring.